Hello, I'm Rachna,
And I'm Vinay.
and we are a team of two, and we are going to present the art gallery problem. Before going into the crux of the art gallery problem, let me pose you this question. How many guards do you think we need to guard a triangle shaped art gallery? Do you really need three guards? In this project, we're going to explore the very famous art gallery problem. This problem is a well known computational geometry problem and it poses the question what is the minimum number of guards needed to observe the entire gallery at the same time? In this problem, the art gallery is represented as a simple polygon. A simple polygon is defined as a polygon that doesn't intersect itself and has no holes. We are also going to assume that the guard has 360-degree view as we see in the animation here. While there are multiple variants of the art gallery problem that explore conditions like the guard walking along a straight line or the guard being positioned anywhere in the polygon, we are going to explore a variant where we are trying to determine the minimum number of guards that we can place on the vertices of the polygon such that every internal point in the polygon is covered. Coming back to the initial question that I posed, we see that for any convex polygon, a polygon where every internal angle is less than 180 degrees, we need only a single guard to cover the entire polygon. For a concave polygon, we see that things start to get a little bit tricky. But we can see that there are some simple concave polygons where we can achieve the entire art gallery coverage with just one guard as well. The main crux of this problem lies with the complex concave polygons. Over here, we see that very clearly one guard isn't going to suffice. So let's overcorrect this issue by placing guards at every vertex of the polygon. We see that this does solve our problem. So going forward, we are going to explore how we can reduce the number of guards that we place on the vertices to get the optimal guard number and placement. We can prove that for any n-sided polygon, we would require at most n by 3 number of guards. Here, n is 10, and we see that 10 by 3, the floor of this is 3. Thus, 3 is the good upper limit for the number of guards needed to guard this gallery, as we see in the image shown here. But interestingly, we can see in this case the guard on the right is useless as the middle guard can see all the area covered by him as well. Thus, the best case scenario for this polygon is 2 guards. Let's aim to prove that we need at most n by 3 number of guards to cover our polygon. To prove the upper limit of n by 3, we need to prove that any polygon can be triangulated. We are going to prove that any polygon can be triangulated or broken up into triangular regions with internal non-intersecting line segments. Why do you think that would help? Here we see that in a triangulated polygon, a guard on a vertex can see all the triangles that are associated with that vertex. The guard can, in this case, see more as well, but their vision would definitely cover the triangles. One of the algorithms used for polygon triangulation is the well-known ear clipping algorithm.
Now, let's talk about the ear clipping algorithm. To understand how an ear clipping algorithm functions, we can start by understanding what are the ears of a polygon. An ear of a polygon is a vertex whose triangle formed by the vertex and its two neighbors do not inscribe any other vertex of the polygon. According to the two ears theorem, any simple polygon with 4 or more vertices would have at least 2 ears. In the ear clipping algorithm, we locate an ear vertex at random and remove it. We also store the triangle formed by the ear vertex and its two neighbors. The status of the neighboring vertices are then recomputed, and the step above is repeated until we have 3 vertices remaining. As we can see, a straightforward implementation of this takes O of n cube time. However, with clever techniques involving doubly linked lists, we shall implement this algorithm of O of n square time. We shall discuss the algorithm steps in a little more detail. At the beginning, we calculate the internal angles of each vertex of the polygon. According to the angles computed, we then label the vertex as a convex vertex or a reflex vertex. Furthermore, a convex vertex could be an ear vertex if the diagonal formed by its adjacent vertices lie completely within the polygon. Coming to the iterative approach of the algorithm. An ear vertex is picked at random and the triangle formed by the vertex and its neighbors is clipped off. Once the triangle is removed, the angles of the neighboring vertices can change as seen in the animation. We thus need to recompute the vertex types of the neighbors and update it. This step is repeated until we have one triangle remaining, after which the algorithm terminates. After the algorithm completes, we obtain a list of triangulated coordinates representing the polygon's triangulation. As we observed in the algorithm, the overall time complexity with the linked list implementation is O of n square. Now that we have talked about triangulating a polygon, let's talk about graph coloring. We create a graph from the edges of the polygon and its triangulation. Interestingly, the type of the graph that is created is a chordal graph. A chordal graph is a subset of the complete graph where any cycle of length 4 or more vertices has a chord inside of it. In other words, the graph consists of cycles with 3 vertices only. Although the graph coloring problem is an NP-complete problem, this category of graphs can be colored in polynomial time of number of vertices and its edges. The algorithm is as follows. We pick any 2 adjacent vertices of the graph and color it. For instance, looking at the graph, let's talk about the colors red, blue and green. Now once we have picked 2 adjacent vertices of the graph, we add this pair to a queue. Now while all the vertices are not colored, and as long as there is an element in the queue, we pop from the queue and color the common neighboring vertices of the pair that is popped. Now once that is colored, we add the pair of colored vertices to a queue. This sort of should remind us of a breadth first search strategy. We repeat this loop as long as all the vertices are colored, or we can think of it as long as the queue is not empty. Once the queue is empty, we exit the loop and the graph coloring is complete. We can observe that no vertex is examined more than once, and for each vertex that we examine, the neighbors are also examined once. This is because once a node is colored, it remains colored and we do not pick it up from any list. Hence, the time complexity is linear with respect to the number of edges and the vertices of the graph. Now that we have 3 colored or triangulated graph, let's talk about how we can use this in optimally placing our cards. Once we have 3 colored, we obtain what is termed as 3 independent sets. What is an independent set? An independent set is a subset of vertices where no 2 vertices of the set has an edge in the graph. Now, to place the cards, we pick the smallest independent set obtained.
In the animation shown, we are picking the subset of vertices that are colored blue through the graph coloring algorithm. In this animation, we can see that the area that is spanned by each card is represented by a unique color. We observe that the total summation of the areas covered by the guards covers the entire polygon. Thus, every internal point inside the polygon is observed by at least one guard.
So far, we have computed the smallest independent set of a 3-colored triangulated polygon. This provides us the exact vertices to place the guards. But let's ask this question whether this is the most optimal in the number of guards that we need. Specifically, we are trying to solve the optimization problem of having the least number of guards possible. But did it solve this? No. An interesting concept in graph theory is that of a dominating set. In the previous slides, we talked about what an independent set is. However, a very closely related set is a dominating set. A dominating set of a graph is a subset of its vertices where every vertex of the polygon is either in this subset that we have chosen or has an adjacent vertex in the set. Speaking of the art gallery problem, this would result in finding the smallest dominating set of the graph for us to place the guards optimally. We shall see in the next few slides that if we are lucky with this randomization, we will yield the least number of guards. This randomization of the ear clipping algorithm becomes crucial for this. Out of the many triangulations that we can form for a polygon, only a few will yield in the smallest independent set of the 3 coloring. As there are n-2 Catalan number of triangulations, which is basically exponential in the number of nodes in our graph, finding that best triangulation that results in the smallest independent set is still exponentially hard with respect to the number of vertices formed. So, to conclude, this would be possible to solve if we had a polynomial time solution to compute a dominating set of a graph. Unfortunately, even for a chordal graph, this is NP-complete.
Now we will look at a demo of our implementation of the art gallery problem. In our implementation, we have classes for point, vertex, and link nodes for our doubly linked list solution. These classes encompass information required for polygon creation. The polygon class consists of a doubly linked list of its vertices and consists of methods to determine the vertex type. We also have utility functions to calculate the angle at a vertex and the area of a triangle and to check if a vertex is inside the triangle or not. For the triangulation, we have a method that implements the ear clipping algorithm as discussed. Specifically, we see the randomized way of sampling an ear vertex from a linked list of nodes. To optimize for time and space, we employ a reservoir sampling technique to sample every node from a linked list with equal probability. In reservoir sampling, we begin by giving each node a probability of 1 by n, here n being the depth of the node in a linked list. Thus, the probabilities of each node would be as we see in the first image, the first one having 1, second having 1 by 2, and so on. Because we exit the loop only when we reach the head of the linked list, we can see that the probability of choosing a node is a product of the probability of choosing the node and the probability of not choosing every node that follows it. Thus, the probability of every node is equal to the 1 by total number of nodes in that linked list. In this example, the probability of choosing node 2 is 1 by 2 into 2 by 3, 3 by 4 into 4 by 5 into 5 by 6, which results in 1 by 6, which is 1 by length of the linked list. We have seen a randomized fashion of choosing ear vertices at each step. With this, we obtain different triangularizations possible for the polygon each time. In the code, we now see how we implemented the graph coloring algorithm just as discussed. Now let's look at some interesting visualizations. This is the polygon that we are going to work with. Now we see this is the image of the triangulated graph of that polygon. And now going further down, we are going to see how the three-colored graph of that triangulated graph looks like. We can choose to put the guards on the smallest independent set of colored nodes from this triangulated graph. In our figure, we have a 15-sided polygon. For this polygon, we know the upper bound of number of guards required is 15 by 3, which is equal to 5. However, we see that we can cover the entire area of the polygon using just 3 guards if they are placed at the location of the blue nodes. Thus, 3 guards at the blue vertices is the optimal solution for such a polygon. This optimal solution is obtained from the randomized process by chance. We need to reiterate that the problem of calculating the smallest dominating set still remains an NP-hard problem for a chordal graph. With this, we have completed discussing the art gallery problem and some interesting algorithms like ear clipping for triangulation and 3-coloring of chordal graphs. We have also discussed a few graph theory concepts such as independent sets and dominating sets. The art gallery problem has a variety of applications in computer graphics, robotics, and sensor networks. Some examples include surveillance, where we see that the art gallery problem can be used to determine the minimum number of cameras needed to monitor a room or a building. The cameras can be placed at the corners of the room or on the walls, and their fields of view should overlap to cover the entire space. We see that it can also be used for motion planning, where art gallery problem is used to plan the motion of a robot in a cluttered environment. The robot can move from one point to another by using a set of guards as waypoints to ensure that it stays within view of at least one guard at all times. Some other interesting applications can be seen in the network coverage area, where it can be used to design sensor networks that can cover a certain area with minimum redundancy. We can also use the graph coloring algorithm to explore the visibility properties of a terrain or a landscape. For example, the problem of finding maximum number of lighthouses needed to illuminate a coastline can be formulated as an art gallery problem. These and many more are the applications of art gallery problem. Hope you enjoyed listening to our video and hope you had fun. Thank you.